This is the Project 4 under title Pulse Code Modulation of Class Communication Theory ecen4242 of University of Colorado at Boulder, taught by Professor Mathis. Here is an introduction about the pulse code modulation. Why do we use this kind of modulation? Well, the pulse code modulation is used to convert the analog signal to digital signal. Well, how it works? It works by sampling and quantizing. Sampling is a mean of replacing a continuous time signal by a discrete sequence of numbers. And quantizing is a mean of rounding off some numeric values to one of the closest permissible numbers or quantized level. As it's shown in the picture on the left here that I got from the book, it's an analog signal that has been partitioned into subintervals or quantized levels. The amplitude of the signal is determined by the midpoint of the subintervals in the sample where it touches the graph. The number of sampling levels is determined by raising 2 to the power of bits that we have. For example, the graph on the right we have a 3-bit quantizer, so we have 8 level spread linearly over the normalized amplitude range from -1 to 1. The quantizer step for a bit is a delta Q equal 2 over 2 to the power of p. The binary numbers show the binary representation of the quantized value in 2's complement. Moving on to the transmitter part of the pulse code modulation, first we have a message sample MK. It's an analog signal that goes through a compander. The compander compresses the signal to produce a continuous amplitude samples at xk, where xk has the shown transform function. Then the signal gets quantized through the quantizer, which produces a serial of bit stream, least significant bit transmitted first. The last block is the pulse amplitude modulation, which converts the received discrete time sequence, which is a bit stream, to a continuous time waveform, S of t. Here it's shown the receiver part of the pulse code modulation. It's pretty much doing the inverse of what the transmitter is doing. The first block is the pulse amplitude modulation, which recovers the discrete time samples, Vn, with rate of Rb from the received signal Rt. And that is because the received signal might be corrupted through noise or through some attenuation through the air. Then the signal Bn gets converted back to binary zeros and ones, then assembled in multiple B bits to form back the binary representation in 2's complement based on the quantization bin that it represents. The B bits then get converted to real value samples, Vk, which is decimal values, using the shown transfer function. In the last block, we have the expander, which undo what the compander did. It expands the signal with the rate of fs, and after going through the computation of finding the inverse transfer function of the compander that's given in the project, I found it to be the transfer function for the expander to be shown in the slide for the expander. For our project, here is the requirements to proceed about achieving the required tasks. First of all of the signal have a sample rate of 8000 Hz and 16 bits per sample that has amplitude that varies or oscillates between -1 and 1. And we have audio files provided in dot wave extension. The compression and expansion have the value of mu 255, or otherwise it's 0 when these two blocks are being bypassed. Thirdly, we have the 8-bit quantizer coded in 2 complement in binary. It has a rate of 64,000 Hz. As if 0 it gets converted to -1, and for 1 it gets converted to 1 which is, in other words, is a polar signaling. Finally, for the pulse amplitude modulation, we have rectangular pulses with amplitude 1 and width of 1 over the rate of sample, which is given in the question, with the sampling rate of 256 hertz, and the first sample starts at negative TB over 2. The first task is to implement the receiver block of the pulse code modulation in MATLAB with a given input signal RFT as a polar discrete time pulse amplitude modulation signal that has sampling rate of 256,000 hertz, as given as an audio.wave files. The results are shown. As we can see on the left, the expander has been bypassed since we have mu equal to 0, and since the audio file test04 is uniformly quantized, we can see also that the signal has a sharp end. While for the results on the right, where the expander has been put into work with mu equal to 255 for test 03, as it is not uniformly quantized, we see the signal to take a sharp of square waveform. Now we can listen to the sound that this is produced. So now we can listen for test 04 and now for test 03. As far as the second task goes, we were asked to implement the transmitter block diagram of the pulse code modulation in both cases, mu equal to 0 and mu equal to 55, with sampling rate of 256 Hz at the pulse amplitude modulation to produce a polar rectangular discrete time signal. Unfortunately, after I spent a lot of time trying to implement this part of the project in MATLAB, I could not get to useful results, as I'm getting some weird signal for the output SFT for my transmitter at the end of the pulse amplitude modulation block. So I could not show any test results for this part. But as being demonstrated in the previous slides about the transmitter part, I understood and I understand what it does and what is the expected results out of it, which is a continuous time rectangular pulse with amplitude 1 with sampling rate of 256,000 Hertz. For this part of the project, we needed to receive one of the signal that is given as an audio.wave file in the project, which is a real human voice and demodulated using our receiver. So after doing that and going and putting it through my receiver, the results are shown. On the left, with the presence of the expander, we can see that there is less background noise in the center when we compare it to the one on the right, which has no expander. We will notice the difference once we listen to the message. So with the mu equal to 255, the sound is...
For man holds in his mortal hands the power to abolish all forms of human poverty and all forms of human life.
And with the mu equal to 0, so when we compare the quality of the two sounds of human, we see that with the expander we get very little or less background noise, which is good for speeches and formal speeches, I mean. For task 4, we were asked to compute the signal quantized noise ratio in dB for two cases with and without the compression and decompression. The equation shown is used to find the SQNR, which is the signal quantized noise ratio, where PM is the average power of the message signal and the PQE is the average power of the quantization error. The quantization error could be found by subtracting the message generated at the output of the receiver from the original message and then computing the average power. Unfortunately, again, this part is dependent on the transmitter as well, and I could not build it in MATLAB based on the fact that I couldn't achieve the desirable results for the transmitter part. So again, I could not do the required computation for this part. If I had the transmitter working, it would have been easy to find the power of the quantization error for each of the four presented signal and then compute the power of each message signal and find the signal quantized noise ratio. Last but not least, for the final task, we had to generate the pulse code modulation, pulse amplitude modulation signal and demodulate them with and without the compression. With the following wave file, I was supposed to use sample 3 given in the project to generate the pulse code modulation through the transmitter and demodulate it in MATLAB and compare the results. I could not get the MATLAB for the transmitter part to work, so the expected result is that it will be similar to what I found for the receiver. The compression helps to reduce the amount of background noise, which is helpful for giving a speech. Thanks for listening. This is the end of Project 4.